Welcome back to the final video. So we will be learning some coding about k-means clustering and then implementing everything. So as I've alluded to in my first video, right, k-means is good for scenarios like these where your clusters are Gaussian with same variance, right? So this is roughly looks like that, right? So if your data is can be embedded into a surface like this, then maybe k-means work pretty well. But if you have data that looks like this, right, then pretty clear you should have one cluster in the middle and then the second guy is on the outside. But if you just run k-means, this will be the result. Okay, so this k-means doesn't really work if you use the typical L2 distance. And if you have Gaussian clusters, but the variance of these clusters are not the same, you will run into problems too, right? So in this case, it's pretty clear that this whole thing is one cluster while this small thing is another. So how do you solve this problem, right? And that's what Euclidean Commute Time Distance help us. So again, the code for this is available at this website, biona/teaching on github.com. So if you want to download this file, this folder, you can do this, copy this link over here, and then go into terminal. Okay, so this, I am currently at desktop. Okay, you can put this anywhere. You can just do git clone and then that do git clone and then this website. All right, so we've just done that. So if you clear the screen, and then there should be a teaching folder. So you move into the teaching folder, clear everything, and then you would have this, right? So you can open up this guy, go to desktop, teaching, and then you can look at things. Whoops, wrong file. This is the file, right? Random graph theory, and then you can actually open the HTML file. So it contains the code for everything. If you want to actually run the notebook, you have to install Julia and you have to install Julia Notebook. Okay. Random graph theory. So the way that I start things is to just do Jupyter Notebook and then the file name. Or what? You do Jupyter Notebook. Sorry. Okay, so you do k-means. So now this is the code for k-means, and we will just clear all the output. Okay. So that we don't do anything. We will just go over this one by one and then see what it looks like. So the first block, we will load all of the packages that we need for this thing. It's pretty limited. Usually it's just linear algebra and then some statistics from plotting packages. And this is my naive implementation of k-means. Okay, I will just run it so that the function is available to us. So the input is a data matrix. Okay, I am assuming that every row is a data point, and I think this is pretty common. And then you also need to input the number of clusters that you want. So what the output is it would output a vector of centers and a vector of clusters that indicating that the first entry of this guy would be the nodes that belongs to cluster 1. Okay, so it initializes some pre-allocated vectors to store what we want, and then it runs 10 iterations of k-means. Okay, every iteration, what it does is it will find the nearest, assign every node to the nearest center using the Euclidean distance. Okay, this Euclidean distance is a naive implementation that I wrote down here. It just tries to calculate the distance between these, the ith entry of this matrix versus the jth row of this matrix, and it does so that there's no memory allocation. And if you're Julia, if you know Julia, this is not a very good way of writing because we are accessing data in row major, but the efficiency is not really too big of a concern right now, right? So you figure out what the nodes, what is the nearest clusters, then you figure out for each cluster what is the best center. Okay, so this is the code that does that, and then you just do this like 10 times for 10 iterations, whatever, and then you return the centers and clusters afterwards. So that is the code for the the naive k-means, right? And then I have some code to compute a few quantities that we want. So the first one computes the adjacency matrix. This is matrix A. Okay, based on the weights of each edge. So you will go through each of the nodes, figure out what is the distance between nodes, and basically find h nodes that, in this case, I tested h is equal to 3. So basically you will find the h closest node to the current node, and then for every node that is closer than h, you will assign the inverse Euclidean distance as an edge weight to the node. Okay, and right here I am saying that every single node is connected. The ith node is connected to the I plus 1 node. Okay, and I ask you in homework to, instead of doing this is not very good. It creates some stability issues. I ask you to, instead of doing this, use the minimum spanning tree. Okay, so you can do Prim's algorithm or basically whatever you want. And then some functions calculate probability matrix, the Laplacian, the pseudo inverse. And finally, we are at this algorithm, right? This is the iterative algorithm to compute the matrix M, the average first passage time matrix. So in this case, I'm saying run. Well, I can just do whatever, right? Run 50 iterations. So estimate M with 50 iterations, or however many you want. You will multiply your thing, put it in storage, set the diagonal to be 0, and then copy it into M. And you just do this however many times. In this case, it's 50, right? And then to get the actual distance, n, right? N comma ij. You just add these two entries up and then square it. Okay. And in order that was the iterative method. So the closed form method is this guy, etc distance. So you input the pseudo inverse L, and then the entries that you want, ij, versus and then you also given the volume of the graph. So if the distance is the same, you return 0. Otherwise, you will basically calculate this guy, right? So it's just a formula in our PDF. All right, so now we are at the code to run k-means using the Euclidean Commute Time Distance. Okay, so it's the same business. You initialize all your matrices that you need, and then you also initialize a quantity, the within cluster variance, and this is used to track convergence. So you will run a maximum of 100 iterations of this k-means etc algorithm, and it's the same business, right? You will find what is the node that is closest to your cluster center, and then you will say all of those nodes will belong to this cluster, right? And the distance will be measured using the Euclidean Commute Time Distance, the closed form version, right? And after that, you will update the cluster centers by finding the most central node. Okay, so the most central node is the place where it is very different than the traditional k-means, because in traditional k-means, you will just look at a cluster and then find the center point of that cluster, and that will be the center of the cluster, right? In this case, the center of a cluster will be a node itself. Okay, but that's still the same thing, right? You essentially just try to find one node inside the cluster, such that the overall distance to every other node in that cluster will be minimized. Okay, so you do that, and then you compute the within cluster variance for the new cluster center, and you say if that variance is small enough than the previous variance, then we declare convergence. Okay, and then you return the centers, your clusters, and everything. Okay, and finally this code is the iterative method to estimate k-means, k-means etc. Right, all of the code down here is the same except for the way that we calculate distance. Right, we will first calculate the M matrix. So this is the average commute time matrix, iteratively estimated using like 50 iterations, right? And this is the distance using that 50 iteration matrix. So everything else is the same. So you have the same within cluster variance and then calculating the variance within clusters, and then you can just run this code. So now we have all the functions, and we will do some experiments. Okay, so let me just do this. So I will comment out these code first, and then I will just look at what the data that I'm simulating is. So the first run in any Julia code will take a long time. A star indicates the code is running, and basically this function is simulating two Gaussian clusters, right? One with mean -4. Oh, what happened? Why is this doing this? What the heck? Sorry, so this is the code to actually run the simulation, right? Okay, good. This is what it should look like. So two clusters, right? Two Gaussian clusters, one with mean -4, one with mean 4. So it's very, very clear there should be no in-betweens. I'll comment this guy out. So this is the code to estimate the FPT matrix, the average commute time matrix, right? I am using, if I use 100,000 iteration, then I am for sure going to get a good enough estimates, right? You can use 150 or you can use whatever you want, right? Just to be sure, we use 10,000 and then we will estimate this thing. So, okay, after 10,000 iterations, these are what the values are. So on the entries that there is no transition probability, it will sort of just keep adding up the ones. I'm not sure if this is expected behavior, but this is what my current code does. So using this commute time matrix, FPT matrix, we can run a bunch of simulations, right? So this is the same simulation. We simulate two Gaussian clusters, run the k-means, run the closed form solution for that guy, and then run the iterative solution. So 3 guys, and then we will display all the plots together. K-means etc undefined. Oh, I didn't run this code. All right, so run it again. All right, so this is the result, right? So the clusters look a little bit, stretched out, but it's because of the axis. Okay, these are still Gaussian clusters, and the clustering basically works reasonably well, right? Everything is kind of the same. So now we move on to the second simulation. Okay, these simulations are places where the traditional k-means is supposed to fail. Okay, so let's just look at what the data looks like. Okay, so this is what before clustering what it looks like, right? You have two clusters that kind of are in this arc shape. These are sine cosine functions. So if any humans would say, okay, maybe this little guy is one cluster and this guy is one cluster, right? And if you run the normal k-means, the etc k-means, using closed form estimation versus the iterative version, right? We will just run the 3 guys, see what happens. Okay, so this is what we get, right? So the traditional k-means will not be able to capture this kind of non-convex shape, right? It would just say, okay, everything over here is in this, everything over here is in this. But the k-means using Euclidean commute time distance is able to capture the connectivity between nodes, right? And that's why we have a correctly clustered cluster centers like these. And because you have the code, right, you can actually play around with these values. So let's say you just pick a different seed, right? What will happen? So if you pick a different seed, this time it also works. This guy never works. Huh. So let's see. If you pick an even different seed. All right, so I guess it like works pretty. Usually, sometimes it might not work. Okay, that's what I'm trying to do. So the reason it might not work is because, okay, well I guess I can't make it fail, but sometimes it's supposed to not work, and the reason why it doesn't work is because we did not compute a minimum spanning tree, right? Remember, we basically just said, okay, every ith node will connect to the i+1, and then you just go through like that. That created some instability. If you test like 100 cases, eventually there will be some instability. So I'm asking you to add in the minimum spanning tree to avoid that case, okay, as a homework. So finally we enter the interesting zone, right? We will be basically we have to figure okay, this will take a long time. Well, let me just look at the result that I have, okay? So this is the code that I ran a long time ago. It's gonna take a while. So essentially we want to know if our iterative version is going to be faster than the closed form version, right? Remember, the closed form version requires inverting this matrix. So if your matrix is big enough, it's going to take intuitively it should take longer, right? As opposed to estimating things using the fast version. So I think in this case I am saying my iteration I will iterate 10,000 iterations. Okay, so that's pretty big number. If you just do 50, I think that should be enough for clustering to work. But 10,000 iterations just to be sure, and you can see that we are pretty fast compared to the closed form version. And obviously, if you look at my code, right, I didn't really try to optimize very hard. So some of these code over here can be improved, especially this guy. So the closed form version, I don't know if this computing the quadratic form in this way is the most optimal. This might create some sort of memory leak because every iteration I will be producing this dense vector, and I'm not sure if that's ideal, but I don't really know a better way to do it at this moment. Either way, this is what we have, and at the homework I think I asked you to do two things, right? So first thing is I want you to compute the minimum spanning tree for every graph. You can add it up. Let's see, where can you add it? You are supposed to implement it inside the ADJ matrix function. So you do it right over here. And the second thing is when you compute the second question that I asked you to do, you can choose one of them, do it whichever. The pseudo inverse of L, I am saying do the inverse of this guy, and then you add in the constant. So instead of doing this, I asked you to do a Cholesky decomposition because you never actually want to do any matrix inversions in the real place, in the first place. So after you do that, then we can see what is the speed gains. Okay. So with that, I would like to thank you guys, and I will see you when I see your homework. Okay. Bye bye.